We are continuing with Utku. It will be also implementation about QFA, but this time instead of photons implementation, here IBM quantum simulators or machines are used. Yes, Utku.
Okay. Hi, I am Utku. I'm from Middle East Technical University in Turkey. I study physics and computer engineering. So just a few bits about this project. This project started as a QIntern project, and it somehow evolved into a Q research project. I believe both our mentors, Özlem Salih and Alba Cervera, are here today with us. And I'm also here. If you are interested in more, you can always check out our archive submission. So let's start with a brief overview of QFAs. So there are actually many models of quantum finite automata, but we use Moore-Crutchfield quantum finite automatons because, well, they are simple and they are simple enough for us to implement in a quantum computer. So basically, they are a 5-tuple. The first component is a set of input symbols. This set doesn't include start markers and end markers, but the automaton uses them. The next is a set of quantum states, which we use in our quantum finite automata. Then we have unitaries, which correspond to each input symbol. We then have a starting state, which we initialize the automata to. And then we have a set of accepting states. The current state of an automaton is traced by a state vector, and then with each new input symbol, we apply the corresponding unitary operator. So a configuration of a given quantum automaton is determined by its quantum state and the next input characters. At the end of computation, we perform a measurement, and if it yields a accepting state, the eigenvalue of an accepting state, then we accept the language, the word to the language, and if not, we say the language is not a part of our, the word is not a part of our language. So for this implementation, we use the same language, so I'm not going to spend too much time on this. Well, basically, we have a bunch of strings in a unary language, and we have a parameter p that is prime. If our language has a if the word has a length that is an integer multiple of this parameter p, then we accept it as a part of the language. If not, then it is rejected. Well, the simplest MCQFA which can implement this language is the following one. It has 2 states, hence it can be implemented with a single qubit. And we start with the accepting state, which is chosen generally as the cat01. Then with each symbol, we apply a rotation that is 2 pi over p radians. And then we compute as such. So one thing you can notice is with words that are multiples of p, we end up in the same 0 state, and since p is a prime, we never end up in a accepting state. Absolutely, unless we have a word that is accepted. Also, as you can see, the error is probably somehow bounded, though this can be a bit high, so we introduce another model. For that model, first we define another 2-state MCQFA. These MCQFA are defined in a similar fashion with the previous one, though with this one, instead of rotating at 2 pi over p radians, we rotate in a multiple of k's, where k is an integer here. Next, we create a 2D state automaton, which the automaton employs d many 2-state MCQFA that I defined in the previous slide. So as you can see in the unitary, the first 2 states that are like 0, 0, 0 and 0, 0, 1, for example, for a 3-qubit automaton, those are applied the R1, so they are governed by the first subautomaton, and the next 2 are governed by the second subautomaton, and like this. So the circuit implementation of these are also important because that's what we are trying to do. The first and the most simple implementation I can list is a single qubit one. So with this one, as you can see, the rotation operator here that we used is really the RY rotation. So with each symbol, we apply an R1 RY rotation. One thing to note here is that just writing the circuit implies that the information of the length of the string is embedded in the circuit. So this is not exactly a automata running, but it's more like a simulation because ideally we want an automaton to react to the input string as it reads. But this is not the case here. One thing to note is since we are using Qiskit to implement them, RY rotations are not actually run in hardware, so we have to transpile it to something like this, to the basis gates that are natively supported by the hardware. Here you see a left-hand marker, which is a SX gate, and a right-hand marker, which are an SX and an X gates. Then we apply a measurement to get all the results. With this implementation, there are several caveats. The notable one being the bounded error is, while bounded, is a bit too high, so we mostly get random results. The second caveat is RZ operations are on IBM hardware implemented as virtual operations, so no real operation is actually being carried while the automaton runs. It's just control circuit computes something, but no real quantum effect is observed. So this is even less of a simulation, so we don't want that. To solve these two problems, we introduced the implementation of 2D states automaton. So with this one, we solve the error of virtual gates with control gates. Since we have control gates, we know that with each character that we read, each symbol, we apply some quantum operation there. Also, since we use many subautomaton, we actually might get a better result. So with this one, what we do is we first put the two qubits into superposition, and we use these to select the subautomata. For example, in this, we first check for 0, 0 and apply the first rotation, and we then check for 0, 1 and apply the second one, like this. However, as you can see, we have, with this order, some non-optimal results. So if we change it to something like a 4-3-1-2 order to check qubits, we can actually reduce the number of NOT gates by 2, which is a rather significant optimization. The next thing we can do is, if you can see the last NOT gate, we don't actually use it to select any subautomata. We just use it to destroy the side effect we introduced. We can remove this by using two blocks like this, and after reading the first symbol, we apply the first block, and the next symbol, the second block, the third symbol, the first block, like this. We switch between them, and if we end up in the first block as the string ends, we apply a NOT gate to the first qubit, and we destroy the side effect. Then everything can work quite well. The next problem with this is the implementation of double controlled rotations. So we actually use get help from Martin Caldas to implement this, and he generously offered us his implementation. He used something like the figure 6a, and since he used an ancillary qubit, this introduced a lot of noise. We used an alternative approach, and we composed controlled double controlled rotations as in the figure B. So now that we introduced a lot of optimizations to the circuits that I have provided, we expect some good results, but that was not the case. In fact, we observed almost a uniformly random results. So with even our 3 qubits optimized version, optimized naive version, we get nothing serious. So this is why we discarded the that implementation. Now, if you reparameterize the circuit, the unitaries, actually we can do a much better job. So instead of applying for separate rotations, we apply this unitary. If you can check, if the first qubit is 1, we apply R3, and if the second one is, we apply R2, and for all cases, we apply R1. So we get 3 independent K values for this one. Its circuit implementation is this. As you can see, we don't have any controlled rotations at this point, so this greatly reduces the number of gates that we have used. So here we list the number of gates that our transpiled circuits have. Unfortunately, during our project, Qiskit changed its basis gates, and we didn't have time to compile the new gate counts, basis gate counts, but this might give you a rough idea how a drastically optimized version improves the runtime. Still, this turns out to be not enough because we don't actually see any improvement. So here you see simulator and real hardware results, and real hardware provides mostly random results, even though the simulator one works correctly. So we see that we need a further optimization. At this point, we run our automata on separate qubits. What this does is this removes the necessity of producing an entanglement. If you look at Qiskit's error rates, the most errors gate there is the C0 gate, and as we remove the necessity for these control not gates, we greatly reduce the error that we have on the circuits. One side effect of this is that as we use superposed qubits, we have a logarithmic space complexity advantage compared to the N1 for a probabilistic, deterministic finite automata. But with a deterministic automata, what you have for this language is you need p many states. So in this implementation, we need k states, d many qubits. So if you were to use this for a very large prime number, then this implementation might still prove to be useful. So this is what we tested, and as you can see here, finally, we have some good results. Both for the word length, P11 and 31, we observe some pretty good measurement results. As you can see, as we increase the number of, as we increase the parameter P, the value of it, we see that our real backend results start to deteriorate. That is mostly because we have a very large circuit depth, but other than this, we actually get pretty good results. So this was all my presentation. I actually talked a bit faster than I anticipated. So we have a few more minutes left. So if you have any questions, I can take them now.
Okay, thank you, Utku. Is there any question? Okay, there is a question. Did you try to pilot tomography?
No, actually, what we do with these plots is, okay, let me reshare it. Nope. Okay, so with this plot, we have, on one hand, the probability of accepting a language. So we want, for the member strings, we want this to be high because we want to accept member strings, but for non-members, we want to be able to distinguish them from non-member strings. So for those ones, we want this probability to be pretty low. So when you consider mode 11, for example, in this graph, the A1 figure 11.a, we have quite successful accepting probabilities for the multiples of 11, but for the other ones, we have low probabilities. So this means that our automaton successfully classifies between a member string and a non-member string. That is also the case somewhat for node 31, though it is not as successful due to the length of our generated circuits.
Okay, there is one question from Andras again from the Discord.
Okay.
In figure 2, why doesn't the transpiler simplify the many gates of the circuit into a single gate?
Well, actually, we conducted these experiments just when IBM changed their basis gates. So currently it does that, but at the time of writing, it didn't do the transpiling as efficiently as we did. So that's why it's worth mentioning. And also it's nice to see how the thing actually runs on the machine. But currently, if you try to run the circuit, it probably produces the same result as we do automatically.
Okay, thank you. I have one personal question. So you also did experiment on the real machines. Was it excited? If so, maybe in which sense? And then maybe after such implementation, you thought, okay, maybe in the future, I would do this, that, or such thing happened or not?
Yeah, well, I'm mostly a computer science person. So I think I find the construction itself a bit more exciting. So maybe you should ask a physicist for that. But also, I think like running something on a real machine was also quite exciting, and the debugging and trying to see how why the things do not work out as planned is a nice challenge. So maybe in the future, I would like to investigate a more sophisticated construct in a more capable machine than a quantum finite automata, because I mean, they are pretty basic. I think investigating stuff like two-way machines and all that, or maybe a push-down automata, I think that would be very interesting.
Okay, thank you very much for this presentation.